Right, so we're going to be doing relations now. This is the second chapter of 11th Math, 11A, and is basically like the chapter right after set theory and is related to it. Right, so before we start off, we should understand what an ordered pair, or more importantly, what an ordered set is. Right, so we denote ordered pairs in this form, right? A comma B with your regular brackets. These should not be confused with open intervals, right? And so, the main important thing to know about these is like it's in this form, right? The bracket A comma B bracket, right, where A belongs to the set A and B belongs to the set B. The most important thing to remember is A comma B is not the same as B comma A for ordered pairs. Order is necessary, and it isn't necessary for A and B to be distinct in this case, right? And an ordered pair is not the same as a set, and an ordered set is an extended version of an ordered pair and is again not the same as a regular set. Example, simple bracket A comma B comma C comma 2 close bracket is not the same as bracket B comma A comma 2 comma C. These are not the same things. And simple bracket A comma B comma C comma 2 close bracket is not equal to curly bracket A comma B comma C comma 2. Not the same things, right? And there's this small property that we should go over. If a1 comma b1 is equal to a2 comma b2, then a1 is equal to a2 and b1 is equal to b2. Right, now let's go over the absolute brain rot, that is Cartesian product of sets. Let's say that A is the set of a1, a2, a3, so on, finite, infinite, I don't care, right? And B is the set of b1, b2, b3, so on. So we're gonna write it as A into B, right, the Cartesian product. And what that's gonna notate is the regular set, the curly bracket set of all the ordered pairs that you can form with the combination of every element from A and B. So ordered pair, right? So it basically has to be that the first element, since A is first, is always going to be some element. Wait, so the first element in each ordered pair must be from the set A, any element from the set A, because A into B is written first here, B into A would be the other way around, where the first element has to be from the B set. So since it's A into B, has to come from the A set, right? So A1, A2, A3, so on for AN, B1, with B1s all throughout the entire row. Then for example, we take A1, A2, A3 again on the next row, but then it's like all of them are B2s. Then you take A1, B3, A2, B3, A3, B3, so on for A and B3 in the next row, and so on. You go on till you get B n. They don't have to be the same number of elements though. So A can have a different number of elements and B can have a different number of elements. So just remember that, right? So this entire grid basically is every combination that you can get from combining one element from the set A and one element from the set B in an ordered pair, right? And if it was B into A, it would be the other way around, where it's like B1, A1, B2, 2, A1, so on, like that, right? And note, this looks like matrices, but it's definitely not matrices. Don't confuse it with that, right? The Cartesian product of any number of sets is the regular, mind you, set of all ordered sets of every combination taking one element from each set. So what do I mean by that? The example we take, A is equal to 1, 2, B is equal to 3, 4, C is equal to 5, 0. So taking A into B into C, we get the regular set of the ordered sets of 135, 130, 145, 140, 235, 230, 245, 240. Right, so it's just going through every possible combination over here. That's it, right? So n of x, as we know, is the number of is basically just going to give you the number of elements in set x, right? And the number of elements in the Cartesian product of any number of sets. So a1 into a2 into a3 into a4 into so on forever till a m, is basically going to be the number of elements in set A1 into the number of elements of NA2 into the number in A3 and so on till AM, right? That's basically just how combinations work in general. So that's what it's going to give you. You can represent every element in the Cartesian product of any m number of sets as a set of points in an m-dimensional graph, as every element in that set is an ordered set. What do I mean by this? Well, let me just tell you, right? So, we have this 135, 130, 145, 140, 235, 230, 245, 240. Do these look kind of familiar to you? Yes, they are exactly like coordinate points. So you could take a three-dimensional graph because we have three coordinates here, right? X, Y, Z, 135, so on. So, you can take every one of these and plug it into the points X, Y, Z value and plot it on the 3D graph. So, you can do that. If you took 4 sets, for example, you would need a 4-dimensional graph. If you did it with 5 sets, 5-dimensional graph and so on, right? Basically, that's all that is about. It's nothing too important. Graphs are not as important in relations as much as diagrams are. So, the diagrammatic representation of some A into B is this. Let me just zoom into it so you can see better, right? So, if you're taking the set 135 and AB, you're basically just going to draw the arrows, 1 goes to A, 3 goes to A, 5 goes to A, and then 1 goes to B, 3 goes to B, 5 goes to B, right? So, you're basically going to get the set, the regular set of all the ordered pairs, 1 by A, 3 by A, 5 by A, 1 by B, 3 by B, 5 by B. And note, you should remember, this is not the same. A into B is not the same as B into A, because why? We are dealing with ordered pairs. You can't, flip it around like that. This is gonna mess things up. And, due to this, we also get as a result that the Cartesian product of A, the Cartesian product A into B intersect the Cartesian product B into A is the empty set, because they will never have any, ordered pair or element in common unless A is a subset of B or B is a subset of A. In that case, there are exceptions, and we come to those. Some of the results. The Cartesian product of A and B union C is basically going to be A into B union A into C. The Cartesian product of A into B intersection C is going to be the Cartesian product of A and B intersect the Cartesian product of A and C. A into B minus C is basically going to be A into B minus A into C, like standard, distributive, stuff like that. And if A into B is equal to B into A, that is, the Cartesian products are the same, then most definitely A is equal to B, right? Because there is no other way possible, right? And A into B intersect C into D is the same as saying A intersect C into B intersect D, right? And if you want to go ahead and prove all these results, be my guest, I don't care, probably go for you though. So if A is a subset of B, then A into A is a subset of A into B intersect of B into A. And if A is a subset of B again, then A into C is definitely a subset of B into C. And if A is a subset of B again and C is a subset of D, then A into C is definitely a subset of B into D. Like, depends on which one's the bigger one, quote unquote, right? Now we actually come to what the chapter was named after, relations, right? A relation is a set of ordered sets whose elements are taken on a certain basis. A pair in a relation can be denoted as A capital R B, where A belongs to the set A and B belongs to the set capital B, and R and taking R to be the set of all the actual relations there, it's always going to be a subset of A into B. I'll just come to that in a second, because all those fancy words sound tough. That's literally why set theory relations are so long. Just unhelpful wording and notation, right? So just gonna look through this with examples, taking the set A is equal to 1 2 3 4 and the set B is equal to xy. And if we take the three these three relations, 1rx, 2rx and 4ry, we get the set R, right? The set of all the relations present between the sets A and B, which is gonna be the relation 1 by x comma 2 by x comma 4 by y in roster form. And this basically means that R will always be a subset of A into B, because if you look at this, these elements are also going to belong in the Cartesian product of A and B, so it's obviously going to be a subset. Now the total possible number of relations for any two sets containing the number of elements m and n for A and B, taking that, the number of total possible relations is always going to be A and B equal to 2mn. And I'm not saying that is going to be the total number of possible elements that's going to be related to the whole Cartesian product thing. This is just the number of relations that is possible. That's it, right? So what this basically means, it can be a bit confusing to kind of think about like how would that work, but then here's the thing, right? So what we're basically trying to say is, like every relation, like 1rx, 2rx, 4ry, so on, all these combinations is basically us taking the Cartesian product of A into B, right? And how many elements is that gonna have? This gonna have m into n elements, so mn elements, yes. And so what basically happens from that is, now looking at the number of possible relations is basically saying how many number of possible subsets can you make out of all these relations that are present here, which like all of the possible relations isn't this. So what are the possible number of relations in total present in the set is basically saying how many subsets can we make out of all of these little relation things in them, which is basically the number of elements in the power set, which is going to turn out to be 2 to the power of mn. So that's kind of how you get it. Again, if you want to try for yourself, please go ahead. I do feel it's going to give you a much better understanding of the topic itself. Now this is in roster form. What's going on, let's just go over the differences, using an example. So let's say we're taking the relation ARB, where R is the relation that B is equal to 1 by A, where small a belongs to the set big A and small b belongs to the set big B, right? And A has elements 1 2 3 and B has elements 1 1 by 2 1 by 3 1 by 4, so on, right? And when we're gonna write all of these, first let's find from which of these elements the relations work out. So 1 and 1 works out, 2 1 by 2 works out, 3 1 by 3 works out. And since we're done with A, we're not going to be taking anything else from B. So these three satisfy the equation 1 by A is equal to B. So how are we going to write this down in a roster form? We're just going to take these pairs and put it in the little set R. So again, it is very similar to how we did it with sets, right? We see the individual elements themselves. However, how are we gonna represent relations in set builder form? We're gonna represent them in a much similar way, where we write this, we take the ordered pair A and B, A belonging to big A, B belonging to big B, and B is equal to 1 by A. And this is the part where we say where each variable, like which set it belongs to normally in set builder notation. And this is the part where we put the relation basis, and for general sets the criterion of how we take it. For the relations example, however, this case that we're taking, it basically shows how B has to be related to A, that is the basis, right? For relation, for all the sets of relations, the basis always has to be how does B relate to A. That is the general basis in set builder form for relations, right? The ordered sets in a relation. And obviously the ordered sets in a relation can be represented in a graphical form as well, because I feel like that's obvious, because it's a subset of the Cartesian product, right? And if you can represent the Cartesian product on the graph, you can represent the relations as well. Now, this can also be represented diagrammatically. Our example over here specifically, taking the sets A and B, draw one arrow from 1 to 1, 2 to 1 by 2, 3 to 1 by 3, and done. That's the diagrammatic representation. Right. And now comes the domain and range of a relation. Right. So, here's the very complicated, fancy set builder notation for this, where the set of A, where the set of A from A and B, where A and B are from the relation itself, and range R, where B from A B from this relation R, right? Did you like, it's pretty unhelpful again, unless you clearly understand the notation. So here I did it in roster form, because roster form is really easy to understand. It's just chill like that, right? So when we're notating, like, let's say R contains the set of the ordered pairs A1 B1, A2 B2, so on till A and Bn, right? So what is domain of R gonna be? It's always gonna be the first element, right? When we're taking pairs, because domain and range, we're always going to be considering that in pairs, because we're taking ordered pairs for these. Ordered sets are a little bit more complicated than that, but basically the domain is always going to be the very first term of the relation itself. So A1, A2, A3, A4, so on. So if you just took those, right, and put those alone in a set, not in an ordered pair separately and then in a set or anything, just those in a set, you're gonna get the domain of the relation itself. The range is basically the second value, right? So the domain is the values that we take in as the input, and the range is all the values that we get as the output. This is gonna be delved more into in functions for now, but this is all you really need to remember. And this really fancy, and all this fancy notation is basically just trying to say this, but in a more generalized mathematical form. It's unhelpful, but it is still useful, because math is math, right? And here's a small note. A relation on set A is said to be a relation from A to itself. In this case, R is a subset of the Cartesian product of A and A into A, basically. Now, inverse relation, which is denoted as R minus 1, is basically R minus 1 curly brackets, the general set of the brackets B by A, where B and A are taken from A and B, which are taken from the relation itself. Again, kind of complicated. The way we're gonna do this in roster form is basically saying, again, let's say we take the set R, which contains all the ordered pairs A1 B1, A2 B2, A3 B3, so on to A and Bn. Then R inverse, the inverse relation is gonna be the set of all the ordered pairs where B1 takes the place of A1 and A1 takes the place of B1. So it's gonna be B1 A1, B2 A2, B3 A3, so on till Bn An. That's it. It's as simple as that. The places are just flipped. That's it. And from that we can derive that the domain of some relation R is the same as the range of the inverse of that relation, and the range of a relation is gonna be the same as the domain of the inverse of that relation. My bad. Right, so the range of a relation is gonna be the same as the domain of the inverse of the relation. Yep, that's it. And we also get that if R is a subset of A into B, as it is, then the inverse relation R inverse is the subset of the Cartesian product of B into A. So B into A, and as we know, A into B is not the same as B into A. And just taking a small example of this, for example, A is equal to 1 to 3, B is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're taking the relation AB, where A belongs from A, B belongs from B, and B has to be 2A minus 1, or basically the correspondent odd number, right? So we have to denote r and r minus 1. This is a little problem I just wrote to best explain this. So we can take we can first find the set r, which is gonna be 1 2 into 1 minus 1, 2 2 into 2 minus 1, and 3 2 into 3 minus 1. That's which is basically gonna give you the set of the ordered pairs 1 1 2 3 and 3 5, right? And basically once you get this, r minus 1 is gonna be flipped. So 1 1, and then there's gonna be 3 2, and then there's gonna be 5 3. That's it. Yeah, it's as simple as that. And here's some stuff I've kept for reference here. The difference between regular sets, the curly bracket sets, or what is more notationally known as unordered sets and ordered sets, is this. In unordered sets, order is not important. Curly brackets a b is the same as curly brackets b a. However, in ordered sets, order is definitely important. So a b is not the same as b a, right? But the advantage of unordered sets in the order is not important part gets cut when you realize that the elements must always be distinct. You can't have the same elements in an unordered set. If there's repeat, they just get kicked off. However, in ordered sets, since the order matters, elements need not be distinct. You can have similar elements, such as we can see here 1 1. So they can be the same in some cases. And your unordered sets are denoted with curly brackets, while your ordered sets are denoted with regular brackets, not to be confused with open intervals. But I feel like you can get that from context. While all sets and relations can be represented in roster form, not all of them can be represented in set builder form. An example of this is the relation 1a, 2b, 3c, 5d, 7e, which is possible in roster notation but is not possible in set builder notation, because alphabets, we don't exactly relate them with numbers as such, so that doesn't work out. And with that, I am done with relations. Thank you.